the last program on the extinction of dinosaurs, we began to look at what sorts of things causes dinosaurs to go extinct. You've got to keep in mind, of course, that birds are still alive, so dinosaurs didn't go completely extinct. But Dr. Tom Rich from the Museum of Victoria began to explore the different sorts of causes, and two theories that he looked at were one caused by volcanic eruptions on Earth, and the second theory was caused by extraterrestrial visitors from outer space. In this day's program, Ceinwen Scutter from Monash University, she's doing her graduate work here, will help us explore the ideas of how volcanic activity, not just the odd volcano here and there, but volcanic activity on a major global scale might have some effect on causing dinosaurs and lots of other organisms to become extinct. And we have a whole series of questions that I want to ask her, and I'm sure she'll be able to enlighten us on them, and then you'll have a chance to grill her when we have our questions later in the program. I think, first of all, one of the questions I'd like to ask is, what really causes volcanoes to turn on? What gets them going, and why do they actually erupt?
Okay, that's a good question to start off with. Volcanoes turn on in a way that we don't really understand very well. One of the major ways that volcanoes turn on is because there's a pressure build-up inside the Earth. And it's just like shaking up a Coke can or a soda can, and we get a build-up of pressure, and when you open that, you get a big eruption. And so that's one of the major ways that we get volcanoes erupting.
Okay, and another question that I have on my list is, volcanoes don't just occur everywhere. If you look at the world and you look at the news reports, you find out that volcanoes occur in New Zealand, they occur near Japan, Mount Fuji is one of those volcanoes. They occur in the western part of the United States, Mount St. Helens is another example. They occur in Hawaii. They don't occur in the middle of the Pacific Ocean, and they don't occur in Australia right now. So what is it, Ceinwen, that determines where a volcano actually blows its top?
Okay. To understand that, we have to really understand the structure of the Earth. So if we start off looking at a model of the Earth and we cut that in half, we can see three different layers within the Earth. The first layer, right inside, is the core, and that's like the core of an apple if you cut that in half. The next layer out is like the flesh of the apple, and that's called the mantle. And that's where the lava comes from, and that's what comes out of a volcano. That's hot molten rock, and that's at several thousand degrees Celsius. And then the outside layer of the Earth, like the skin of the apple, is the crust of the Earth. And that crust is very, very thin, and when we get a break in that crust, we can allow mantle out to the surface, and that allows a volcano to occur. Now, there's only breaks in certain places on the Earth, and if we look at a map, we can see the distribution of these like you were talking about. And you can see that there's volcanoes concentrated along the edges of these fractures in the outside of the Earth's crust.
So the Earth really, that thin skin that you're talking about, the crust, is divided up into a series of really big plates. And it's only along the edges of those plates that this volcanic activity, and earthquakes for that matter, and real hot parts of the Earth occur. So that kind of makes me think, how does that all relate? What kind of theory has been put forward by geologists in the recent times to explain why those plates exist and why the volcanic activity and the earthquake activity occurs there? Could you give us a little idea of that? What's the name of that theory anyway?
Yeah. The name of the theory is plate tectonics, and that was first discovered when people realized that parts of the Earth do fit together like a jigsaw puzzle. The west coast of Africa and the east coast of South America fit together like a jigsaw puzzle, and so when you move them together, you can see that those two edges of the continents used to touch, and they've moved apart. And so we understand that the ocean has formed over time as a fracture down the middle of the Atlantic Ocean, and as those two continents have moved apart, we've got volcanoes down the center, and that's formed new crust.
Yeah, well, that's like mid-ocean ridges. Mid-ocean ridges are the lines along which there's a lot of volcanic activity, a lot of earthquake activity, and such things as that, and that's where volcanoes are occurring along that break. Now, there's a difference in the depth of the earthquakes that are associated with that volcanic activity, and that kind of tells us that the kinds of breaks between those major plates are not all the same. There's, as Ceinwen said, down the middle of the Atlantic Ocean and in the eastern Pacific Ocean, there's a ridge where there's volcanic activity. It's going on there. There's what we call high heat flow, so it's a pretty hot spot on the Earth. And there's very shallow earthquakes along that. Now, in Japan, it's a different kind of volcanic activity in a way, and different kinds of earthquakes. Could you explain a little bit about that?
Okay. That's a different type of boundary. Where the two plates in the mid-Atlantic are moving, they're moving apart. Whereas at Japan, they're moving together. And because they can't just bang into one another, one has to move below the other. and that's called a subduction zone. And we can look at a picture of that as well. And so the earthquakes there are much deeper because there is one of the plates is moving much further underneath the other, and we get a different type of volcano there as well.
Yeah. Can you tell us the difference between a mid-ocean ridge or an ocean ridge volcano and a, say, Japanese volcano, which is over one of these down-going subduction zones? Because there's a real difference in how they affect people and in their intensity.
Absolutely. The ones on the mid-ocean ridges erupt a much runnier type of a lava. They're much lower in silica. One of the types of lava that these would erupt is this basalt here in front of me. So this is basalt. This is formed at an ocean ridge. It's a really runny type of lava, and you can see that on the surface. You can see these nice ropey surfaces. Pat's going to show us the other type of volcanic rock, and that's much higher in silica, and we can see that by the colour as well. That's a much whiter rock compared with this black rock. So that's one of the differences between the two different types of volcanoes. They erupt a different chemistry or composition lava. And one of the other differences is that the volcanoes in Japan are much more explosive than the ones at the mid-ocean ridges, so that they erupt smaller pieces and they get thrown much further into the air, so they have a bigger effect on people than the ones at the mid-ocean ridges.
Yeah, you never would want to go out and spend too much time on the edge of one of these Japanese volcanoes, because people get killed doing that.
Absolutely.
Whereas you can go to the ones in Hawaii, and lots of people spend a lot of time standing around watching what's going on there, under controlled conditions, but certainly it's not as dangerous to do that. So there's difference in chemistry, there's difference in how they affect people and how the volcanoes erupt. Now I guess what we're really getting at the moment is how does all this affect dinosaurs and other animals through time? And is there one kind of these volcanoes that seem to be the ones implicated more, or what I mean by implicated is that are more likely to cause extinction of organisms than the other?
That's right. Surprisingly, it's not the really explosive type of volcano. It's not the one that's most dangerous to people. It's the one at the mid-ocean ridges which erupts the basalt. And that's because these types of eruptions have a very noxious gas emitted, and that's very dangerous to organisms.
And there's also the volume that's involved in in that kind of eruption. The volume of volcanic material put out, I would presume, in something like the mid-ocean ridge volcanism, is much greater, isn't it, Ceinwen?
Yeah.
Than it would be. That's
right. One of the classic cases of this type of volcanism in the past covered an area as large as Eastern Australia, Queensland, New South Wales and Victoria all together. So that's an incredibly large lava flow, and that would have very drastic effects on animals and plants living at that time.
Now the two times that we'll look at in the second part of this program are going to be the Cretaceous, the end of the Cretaceous, and everybody remembers the Jurassic. Well, the Cretaceous is just after the Jurassic. And the time period between about 65 and 67 million years ago, when lots and lots of things, not only dinosaurs, but lots and lots of other things became extinct. And to contrast that, we're going to go back further in time and look at another major extinction, which may have had different causes than the Cretaceous extinction, and that's the Permian, which was about the end of which was about 245 to 248 million years ago. And we're going to look at it specifically from what volcanoes could have had to do with this. So that will be in the second part of the program. I guess the few other little questions I have to ask is about these extinctions is when these extinctions occur, or when we're looking at these extinctions, what are the things that volcanoes, we've touched on them, but what are the things that volcanoes do that are likely that we ought to be thinking about with regard to how they can cause extinction? You've mentioned nasty gases. Can we look at nasty gases a little bit more?
Sure.
And talk about these nasty gases. What are they, and what will they do that might cause the extinction of dinosaurs?
All right. One of the nasty gases is carbon dioxide. Another one is sulfur type of dioxide, and these are both emitted in volcanic eruptions. There's also what's called a halogen, and they're chlorine and fluorine and other elements like that. And they all combine in different ways in the atmosphere to create a fairly difficult environment to live in. So carbon dioxide can turn into a type of acid, which then comes down as acid rain, and so that's pretty unpleasant for animals and plants living there. The sulfur will combine with things in the upper atmosphere as well, and we're going to actually get a cooling of the atmosphere. The actual temperature of the Earth will lower, and so this will be a very different type of environment to live in.
So it's going to become cooler right at the time of the volcanic eruptions, and you're going to have all these nasty things like acid rain and just bad smells around, which maybe they're worse than just bad smells, or things that can actually be poisons in the near vicinity, and maybe not even just the near vicinity, hundreds and hundreds of miles downwind from where these big volcanic eruptions are occurring. There's also another thing that volcanoes do besides just the nasty gases, and that's the crud they throw up in the air that's not just gas but particulate matter. Now, how can that affect dinosaurs?
Yeah, well, what that will do is throw up all these tiny particles like this in front of me here. So this is the particulate matter that Pat was just talking about, and these are small fragments of ash that come out of a volcanic eruption. And when these move into the atmosphere, they form a type of blanket, and it makes it very difficult to breathe properly, and the sun's rays don't get through properly. And this is like the greenhouse effect that we've talked about in the past with aerosols in the atmosphere, and it basically will cause some kind of stopping of the Earth's atmosphere, of cooling and warming properly.
Yeah, so I mean, you get that up there, and it does take out a lot of the energy it doesn't allow energy in that's warming the Earth, and so temperatures cool, climate's cool, and things happen. And in a way, it's just the opposite of the greenhouse effect, where you get energy coming in and not being allowed out. This doesn't allow the energy to come in. That pretty much finishes the first part of this program, where we looked at volcanoes and how they're related to things that can cause extinctions of organisms. The second half of the program we'll look at two very specific times, and now we open it up to you to call or fax in and ask us questions about the first part of the program, and Ceinwen and I will do our best to answer them. So we're waiting to hear from you. Well, we have a few questions here, and we'll do our best to answer them in about the next 10 minutes. Chris from Warrigal North Primary, what's your question?
Did humans evolve from dinosaurs?
No, they didn't. Humans came from another group of reptiles. So dinosaurs were doing their thing while the mammal-like reptiles that gave rise to our line were doing their thing. Okay, we have another question. Thanks for that, Chris. From Trent at Diamond Creek Primary School. Trent?
My question is, what effect did acid rain have on the dinosaurs and other animals?
Okay, I'll ask Ceinwen to answer that.
Okay, thanks, Pat. Acid rain, it's very acidic, so when it falls on the ground it will kill vegetation and it will kill some of the plants and other animals that the dinosaurs would have eaten, and so that would have made it very difficult for the dinosaurs to live. Have you got any other points?
Well, the other thing I would say is that that acid rain would change the chemistry of freshwater streams and of the ocean ultimately, and that can just even a little bit of change in the acidity or the basicness, in other words the pH, can make a big difference on what animals can survive. That's not the dinosaurs, but the dinosaurs ultimately depend upon other groups of organisms like the plants and other things. So that's many ways that it can affect them. We have another question from Jacqueline at St. Andrews Primary. Jacqueline?
The question is, when a volcano erupted, could that have triggered an ice age which would have led to the extinction?
Yes, Ceinwen can give us a little bit on that. Yeah.
It could have.
It could have triggered the extinction.
Yeah. So it's a similar sort of thing we were talking about before. We've got particles in the atmosphere that would have caused a cooling of the world, and so the animals wouldn't have been able to live properly in that. And we have acid rain, and we also have the noxious gases that we were talking about before. So it would have been a difficult atmosphere for the animals to breathe and also the plants to live in.
Keep in mind, too, Jacqueline, that some animals weren't affected by it. There were things like turtles and some crocodiles and lots of things that got across that thing we're calling the Cretaceous Tertiary or the KT boundary. So not all animals were affected by it, but a lot were, and plants as well. Thanks for that. Morgana from Christ of King Geelong.
Where was the biggest volcano eruption? Where was the biggest volcano eruption in the dinosaur period, and did it destroy any dinosaurs?
Well, I'll let Ceinwen do most of that, but of course, any time you have a volcano erupting, the animals right around that are really going to get blasted. So immediately around volcanoes like that, they're certainly going to get knocked out. Now, Ceinwen's going to have to tell you where the biggest volcano was.
Okay, the biggest one at the time that the dinosaurs were killed was in the Deccan Traps, and that's in India. And we'll look at a map of that and be able to establish exactly where that was in the world. And that was a huge eruption that covered about half of India, and that would be equivalent to most of New South Wales and Victoria. So if you can imagine a volcanic eruption that large, that would have a really big effect on dinosaurs and other animals and plants.
Yes, and in the second part of this program, Ceinwen will show you where those volcanoes are, so that will be coming up. Now, we have some faxes that have come in. A fax, many questions from St. Patrick's Primary School. We'll start out with Holly McDonald. What gave you the idea that volcanoes killed the dinosaurs? Ceinwen, that's yours, your volcano.
Okay. All right. Our idea was because we noticed that the extinction occurred about 65 million years ago, and we discovered from looking at the age of the rocks, the volcanic rocks that formed at that time, they were also about 65 million years ago. And so we sort of thought, well, they were occurring about the same time. Maybe there was a relation between the two. Maybe the volcanic eruption did cause the extinction of the dinosaurs at that time.
And I think what Ceinwen's pointed out, Holly, is something that you use in science a lot, is you look for things that occur at the same time or that correlate somehow, are telling you that these two things are happening at the same time. And that makes you think a little bit more about, well, we ought to look into this. We ought to think more about it and see if there is some relationship. Joshua Wilson from year 5 at St. Patrick's, are you sure that this is the way they died? Well, of course, we're not sure. Anytime you're looking in the past and you have to try to figure things out, you don't have a time machine. If you had a time machine, it would make it surely a lot easier. But you basically try to figure out the best explanation you can on the basis of the information you've got. So no, we're not sure, but it's a theory, and it's the best theory we've got at the moment. Another couple of questions. Nicole Madden, year 5. How can you tell the difference between dinosaurs' bones and other bones? Well, you can do that if you spend your whole life looking at bones. And you begin to look at the shapes of the individual bones, and you know the difference between a turtle and a dinosaur and a bird simply because they have different shapes. But it's not something that you can just walk out the door and learn really quickly. You have to spend a lot of time looking at bones of all these different sorts of animals. We have another question on telephone from Chris from St. Patrick's Primary School in Stall. Chris, what's your question?
Why do tectonic plates move, and do the edges of the plates change position quickly?
Okay, I'll give that one to Ceinwen, Chris.
Okay. The tectonic plates don't move that quickly. They're moving on the mantle. So the mantle, if you imagine, is like a big area of liquid, and the plates are moving like ice blocks along the surface, and they move because the liquid of the mantle is moving underneath. It's what we call convecting, so it's moving in a sort of circular motion underneath. So the plates move along on top, and the edges of the plates will move together. And some of these are moving at fast rates, maybe 12 centimetres a year. In parts of the Pacific, the plates are moving apart. And other places, they're moving together quite slowly. That only might be 1 or 2 centimetres a year. So I'll pass that back to you, Pat.
Okay, and I have some more questions on volcanoes here, which we'll get Ceinwen to answer. This is from Essex Heights Primary School, from Philippa. Why, when you held up the two pieces of rock from the volcano, were they two different colors? So you're talking about the tuff and the basalt.
Okay. The basalt we were looking at is low in silica, and that gives it quite a black colour. It's volcanic glass, and so that's why that was a dark rock. The other rock that Pat held up, the very light rock, it was white in colour. That's because it's high in silica, and because it's high in silica, it means it has a mineral called quartz in it, and quartz is very light coloured, and so it gives it a light colour overall. It's just a difference in chemistry between the two rocks.
Okay, I'm going to keep giving Ceinwen some more questions because we have a lot of volcano questions coming in here. Nicholas Ford from Essex Heights Primary School again. Was the Earth smaller before the dinosaurs lived on Earth than now because of the volcanic activities and plate tectonics? That's a very good question.
That's a great question, Pat. You might have got me here. The Earth hasn't really changed in size over time much at all. What's been happening is the plates do move apart in some areas and they move together in others, so that where in one area we might be actually creating new land and new rocks because the plates are moving apart and we've got a volcano. In another area they might be moving together and the plate gets consumed and used up and then recycled into another volcano again. So we're not really changing shape over time.
Okay, another question coming in from St. Francis Xavier Primary School from, I don't see the name of the person, but you'll know who you are. One of the questions is, which Australian dinosaurs were affected by the mass kill at the end of the Cretaceous? We actually don't know, and the reason we don't know is because we don't have a very good record of dinosaurs at the end of the Cretaceous in Australia. We have things from the early Cretaceous, and we have just a few things in the very early part of the late Cretaceous, if that makes sense to you, but we don't have dinosaurs right on that boundary, so it's very difficult to tell. And another question, why did the Earth fissures move? Why do, I guess what the question means is, why did the boundaries between some of these plates move?
Okay.
I'll give that to Ceinwen.
Yep. Okay, well, they're only moving apart in one locality, so that when I was talking about before, we might have the convecting mantle. That means that the hot liquid rock is moving up underneath a plate, and that can form a fissure or a break in the Earth's crust, and that will form a new fissure there.
Okay. It's about time to stop answering these questions. Not that your questions will eventually be answered. We'll get back to you on facts, but we're going to have to go on now to the second part of the program, and then you'll have another chance, and we may be able to answer some more of these questions. So thanks for all those questions. We're going on to part 2 now. Well, welcome back to the second part of our program on how volcanoes affect extinction. And what we're going to look at in the second part of the program is 2 times in the past, one about 65 million years ago and another one about 248 million years ago, when there were really, really big extinctions of lots and lots of different animals. Of course, you all know that 65 million years ago, the dinosaurs, or most of them, snuffed it. But you may not know so much about the 248 million year extinction at the end of the Permian. So we'll look at those 2 times, and we'll look at when there was volcanic activity and if it might be the culprit that helped knock out a lot of these different animals. I think before we begin that, though, I want to bring this a little closer to home. As you remember when Ceinwen was talking about the kinds of volcanic activity that causes extinctions, or that might be implicated in them, she said something to the effect that there were these big outpourings of flood basalts. Now, we have some of those very close to home. They're quite young, but just to give you an idea of what they might look like, I might ask Ceinwen to show you some rocks from a place very near to Melbourne, in Victoria, in the Western Districts, and show what kinds of rocks these kinds of eruptions, these kinds of mass flows produce, so that you will have a better idea of what they look like. So if Ceinwen, you could show them what the Western District volcanics look like.
Well, what we've been looking at with the lavas so far are lavas from Hawaii, and that's a similar type of basalt eruption. In Victoria, we've had much larger basalt eruptions. Like you're talking about flood basalt, that just means much larger volumes. And some of the other types of rocks we get from Victoria are these bombs here. Now, the reason we call this as a bomb is because it's been thrown out of a volcano at quite high speeds. And we can see that this outside black part was molten when it was thrown out because it's got these two funny little tails on either end, just like a helmet. Now, this rock's really, really heavy. That's why I'm not lifting it up at the moment. But we can have a look at what is inside it, just here. And you can see this green crystal. And this green crystal is a type of mineral called olivine, which has come out of the mantle, the inner part of the earth that we were talking about before. And you can see on the outside of this piece, this black skin, which is the lava. When it was thrown out of the volcano, it became attached to the green crystals. And you can see the crystals inside are much larger, and you can't see crystals in this outside black skin. Now, the reason for that is because the crystals inside cooled much more slowly, so they could grow to a much larger size. And the lava on the outside cooled almost instantly when it was thrown out onto the Earth's surface. And so that's actually what we call volcanic glass. You can't see any crystals in that at all. And we can actually tell how deep this rock has come up from below us. It's actually come from about 40 kilometres deep below us in the mantle.
Well, that's really cool that you can actually see something you can put your hands around that's come from that far underground. It's not just theoretical, what we think about the inside of the Earth, but we actually have samples of it.
That's right.
So really close to home, we've got material that is very like other material that Ceinwen's going to talk about shortly from India and other parts of the world that may have produced all this nasty stuff that had something to do with dinosaur extinction. And so for the rest of this program, we're going to look at these two times that we spoke about earlier, one in the Cretaceous about 65 million years ago, and another one in the late Permian about 248 million years ago. I might mention at this time that the information that Ceinwen is going to talk to you about of the extinctions of about 248 million years ago is really hot off the press. It's something I wasn't even aware of when I came in here to the program today to film, that there is a lot of volcanic activity about that time. It's major, major volcanic activity. That Ceinwen's told me that it's the most major volcanic activity of this sort really in the history of the Earth. And it is also the most major extinction that we've got. So that's very interesting. So let's begin by looking at the Cretaceous. The Cretaceous is right after the Jurassic. It ends about 65 million years ago, and at the Cretaceous tertiary boundary, which is called by scientists and a lot of media people the KT boundary, there was a big extinction of dinosaurs. But it wasn't just dinosaurs that went extinct. There were lots of marine animals, both animals with backbones and lots of microscopic animals. A lot of the plankton went extinct at that time. There were lots of other vertebrate animals, or lots of other invertebrate animals, animals that didn't have backbones that went extinct at that time. So it was a pretty major extinction. People are still arguing at the moment, and we'll discuss this in the next program, but they're still arguing about whether this was a gradual or a very abrupt extinction, and that has not been resolved. But taking into account the factors that might have caused it, we want to look at what volcanoes could have had to do with this kind of extinction. And I'd like Ceinwen to give us a briefing on what was going on with volcanoes about 65 million years ago on a world scale, where we had some of these big flood basalts like the ones we were talking about in western Victoria, and how, again, that might have affected the extinction of lots and lots of organisms, both on land and in the sea.
Okay. The major volcanic outpouring at that time was occurring in India, and that's our second largest flood basalt eruption in the world. Mm-hmm. So that will be really interesting to look at the size of the extinction that you're talking about at this time as well. So that's our major eruption, but there were many other eruptions occurring at that time.
Mm-hmm. And where were those? Were there some here in Australia, or were...
Yeah, there was some going on the eastern coast of Australia, up in Queensland, so we can look at some pictures of that as well, some of those volcanoes. And they were happening about the same time and for about the same reason. We're having the type of volcanism coming up from the mantle and causing basalt lavas to erupt on the surface.
And so then again, just to review what we said in the beginning of this program, what did that mean as far as dinosaur extinction? What was it about those eruptions that might have caused the dinosaurs and other of their friends, and not friends to go extinct?
Okay, well, we had really large volume eruptions at that time, and they were emitting noxious gases such as sulfur, carbon dioxide, chlorine and fluorine, and these were getting into the atmosphere. We also had particulates, so the type of ash that was coming out of the eruptions, and that was cooling the Earth in general and creating a fairly noxious atmosphere for the people to live in, for the animals.
And also, as you were saying earlier, the particulate matter was, this cooling was a major thing. And we know from looking at oxygen isotope data, we're not going to go into this in this program, but we do know that there is a correlation, there's a relationship between the ratio of one kind of oxygen isotope to another in the surface waters of the ocean, it's correlated with what the temperature is. And we do know that at this time temperatures were falling. It was getting cooler on Earth. It had been very, very warm prior to this time, and then temperatures began cooling. What that's due to, we're not absolutely sure, but as Ceinwen is saying, it could well be due to a lot of particulate matter, like the ash that she showed you in the first part of the program, being chuffed up in the air, and that then reflecting the incoming sunlight, which meant a lot of that energy that was coming in was bounced back into space, and the Earth never really got the advantage of it. So cooling, nasty gases, and also some other things. If there were lots and lots of volcanic activity, of course there's the possibility of wildfires. And at that time, there is a great deal of evidence in different parts of the world. There are very big charcoal layers that indicate that there were wildfires going on at that time, which would have devastated forests, certainly within close range of the volcanic activity. And if it was on the scale, such as the Deccan Traps in western India, that is a really large part of India. It's not just, a few square miles, but it's hundreds and hundreds and hundreds, even thousands of square miles in India.
Yeah.
So that is one extinction that is really, there is certainly volcanic activity going on at that time, and we know that animals became extinct. Whether that was what caused it is still being discussed. Now, there's another time, too, that we were talking about, and that's the Permian, about 248 million years ago. And as I mentioned, I was not aware until I walked into the studio this morning, and Ceinwen enlightened me on this, that there was another major phase of volcanic activity on a global scale at that time. The animals that became extinct at the end of the Permian were different than the dinosaurs. Dinosaurs weren't around at that time, but there were major extinctions of all backboned animals, the ones that were living in terrestrial environments. And there's estimates of up to 85% of marine organisms went extinct at that time. So I guess something that we could investigate with this is how we've talked about dinosaurs and terrestrial animals, and how those animals and their extinction could be brought about by volcanic action. And you can think more in terms of, there's the volcano and there's the air and it's filled up with horrible, nasty gases and particulate matter and so forth. Well, how can it affect organisms in ocean waters? Can you give us some idea how that might happen?
One of the things I was talking about in the first part of the program was the formation of acid rain, because we've got carbon dioxide in the atmosphere, and that will fall into the oceans, of course, and that actually changes the acidity of the ocean water. And we also get changes in the chemical composition, and that can make it a very difficult environment for specially evolved organisms to live in.
Because many times the organisms of any sort are very specialized for the job they do, and so even a minor change in the chemistry or the pH, which is the acidity or basic nature of the water, can make a great deal of difference, particularly those organisms that are living in the surface waters. Now, the other thing, too, that Ceinwen's talked about that could be could have an effect is just the change in temperature. Just the temperature, a few degrees, maybe 1, 2, 5 degrees change in temperature, which would have been caused by the cooling, because the particulate matter from the volcano was up there. All of that could have had an effect on the marine life. I think, just to give you an idea of what some of the organisms that were around at that time looked like, there's a slab of plant material that we have from northern New South Wales. This slab here from northern New South Wales has a whole bunch of leaves on it of a group of plants called seed ferns. These were really tough plants because they lived in an environment that was extremely difficult to live in at the end of the Permian. Yes, these were very tough plants, and the reason they were tough is they were living under very, very cold conditions, even in New South Wales. Right here in Victoria, up at Bacchus Marsh, there were great glaciers. They were not just your average little valley glacier like you find in New Zealand today, but they were continental glaciers upwards of 10,000 feet thick. those glaciers were around because the climate was very cold. And again, the particulate matter that had been chuffed up in the air by the volcanoes may have been the culprit that caused the Earth's whole climate to cool. So that brings us to the end of this program. I hope you have a better idea of at least one culprit that might have been involved in bringing about the extinction of the dinosaurs and many things before them. There may be some repetition to this through the geologic timescale. It's something that lots of people are looking at. And in the next program after this, we'll be looking at extraterrestrial implications and extraterrestrial invasions that might have also worked either alone or together with volcanoes to bring about these extinctions. Now it's your turn to ask us questions, and Ceinwen and I are just here waiting to get your calls and faxes because we love every question that you send to us. So we're waiting for you to call us up. Okay, we have quite a few questions here. I've got a stack of faxes and a lot of phone calls. We'll go to the phone calls first. Daniel from Warrigal North Primary School. What's your question, Daniel? Is Daniel there? Okay, we haven't got Daniel on the line. We'll take Warren from Diamond Creek Primary School. Warren? We're having some problems with these phone calls. I might go to some faxes and we'll come back to the phone calls. Why has the question from St. Andrews Primary School, why hasn't the volcanic eruption happened again? I presume you're talking about these great big flood basalts we were referring to in Siberia and the Deccan, and I'll pass that across to Ceinwen.
Thanks, Pat. There's been quite a few of these large flood basalt eruptions since the large one in the Deccan Trap 65 million years ago. There was one at the Columbia River basalts in Northern America, and that happened about 15 million years ago. And that probably would be linked with another extinction. We could look at the timelines and see if there were other extinctions occurring at that time. We also have had some very large basalt eruptions in Victoria. We've got the third largest basalt flood basalt field in the world in Victoria, and that's all from Melbourne through to Adelaide, so west of Melbourne. There's about 400 volcanoes there, and that could have had some kind of extinction linked with it as well, perhaps.
Mm-hmm. The thing about the volcanoes in Western Victoria is that that field is not dead. A volcano could erupt out there any time. It's still hot, and the last volcano that erupted out there was about 4,000 to 5,000 years ago, so it's an interesting place. We'll go back to the phone calls again. Daniel from Warrigal North, have we got you now?
Hi.
Hi.
I was just wondering, how did you know if the dinosaurs are meat eaters or plant eaters? Because humans weren't there.
The best way is, again, you have to know a lot about modern animals, and their teeth are the giveaways, or whether they have really curved claws, curved, flattened claws, and things like that. So it really comes down to comparative anatomy. You look at modern animals, and you study their diets, and then you apply that to past animals. You would have no problem mistaking Tyrannosaurus rex for somebody that ate oats, I can tell you. His teeth are big and sharp and modified just for that kind of thing. So it's modern comparative anatomy. Thanks for that. Warren, Diamond Creek Primary School.
Yeah, I was just wondering, are the basalt crystals that come out of the volcano, are they valuable?
Okay, I'll give that to Ceinwen.
Thank you, Pat. The olivine that we were looking at before, it doesn't really have a value in terms of diamonds or sapphires, something like that, but it has a lot of value for us as scientists because it tells us something about the inside of the Earth. We can't actually get down to the mantle, but we can get this evidence which has come out of a volcano and shows us what conditions must be like in the mantle. So in that way, they're very valuable, even though they're not worth a lot of money.
Okay, thanks. Warren, let's see, Matthew from St. Paul's Primary in Bentley. Matthew?
Well, I'd like to know, how was the mantle actually came to exist in the first place?
How come the mantle came to exist in the first place? That is a very good question. I'll let Ceinwen try to answer that.
Glad you're going to let me try. When the Earth first formed, it was a group of gases, and over time it's evolved into a whole lot of different layers. So the very heavy metals have moved into the core, and that's things like iron and nickel. And then the next layer out is the mantle, which is all the molten rock, and they're all pretty much silicate minerals. And the crust is just the cool outside part of the mantle. So it's happened over billions and billions of years. It's just changed from the original gaseous form.
Okay, thanks, Ceinwen. Another question that came in on a fax from Andrew at Donald Primary School. Do the plants grow back after a volcano has erupted? Yes, in fact, they do. And in fact, volcanic soils are some of the richest soils in the world. Lots of studies have been done on places like Krakatoa, which blew its top last century up in the Indonesian area, of the succession of plants and animals that come back onto these islands, and we know a lot about that. So volcanoes, even though at the time they erupt, can be terribly devastating, the material that's blown out of volcanoes can produce very, very good soils. People like to grow things on it after a few years. Okay, Susan from St. Clair's Primary School in Box Hill, what's your question?
If there were other animals, how come they haven't been introduced yet?
If there were other animals, how come they haven't been introduced yet? I don't understand that question. Can you go through again?
Because you said on the TV before that there were other animals that died in the volcanoes, but how come they haven't been introduced yet?
Well, a lot of times if you just have a local volcanic eruption and the animals are killed right around that volcano, after the volcano is basically switched off, the things that were further away from the volcano that didn't get killed can move back into the area. So that's how that would happen.
Yes, and how did the dinosaurs die if there were only small volcanoes in Australia?
Well, because volcanoes, like Ceinwen was talking to you about the Deccan Traps, that affects global climate. So even if there were no volcanoes, although there were some in Australia at that time, they may not have been the things that were the culprits. The big volcanoes were in India. It affects world climate because it cools it off. So that even if volcanoes are erupting someplace else in the world, it affects the whole world climate, and that's the thing that's important. Okay, thanks, Susan. Brendan from Witcham Primary.
Hi. I'm just wondering, do you know how a volcano started from scratch?
How did volcanoes start from scratch? Okay, Ceinwen, that's in your ballpark.
Thanks, Pat. Okay. Volcanoes just start, as we were talking about, with the mantle starting to convect, and we get a pressure build-up under the Earth, and that actually forces a break in the crust of the Earth, and it moves out. Now, the reason for the volcano actually occurring in that place can be a whole number of different things. You can have the fact that the mantle is moving up, and that makes the crust quite weak in that spot, and that can cause a volcano there. And another reason is an area like Japan, where we were talking about one plate moving under another. the first plate moving under the other plate will take a lot of seawater down with it, and that makes the mantle there under a lot of pressure, and it will push out and form a volcano there. So we've got a couple of different reasons for volcanoes to form.
Okay, another facts we have from Waldow Primary School. One of the questions is quite interesting. It says, do you believe in alien life forms? Actually, scientists don't believe. Scientists actually go out and actually look for things and bits of information and try to piece together a theory. And we have absolutely no evidence whatsoever that there are any aliens with the dinosaurs or any aliens out there. So unless we have the evidence, it's very hard to put a theory forward that there were aliens. There's a number of other questions asking about how they might have affected dinosaurs and such, but since we have no evidence for them, we would really not be theorizing about how they affected the dinosaurs. But it's an interesting question. Lisa from St. Patrick's in Stawell. Thanks, Lisa.
How far around the explosion do volcanoes poison or affect?
Okay, I'll let Ceinwen say something about that.
Thanks, Pat, again. Okay, as Pat was just saying before, when a volcano erupts, a very large eruption, that will affect global climates, so that it's going to affect right around the world. Some people might remember that when Mount Pinatubo erupted in June of 1991, we got great sunsets in Australia, and they were shown all around the world. And that was because there were these particles, ash particles, up in the atmosphere, and that caused the great sunsets. So it will actually affect the entire world if the volcano can erupt the ash particles high enough into the atmosphere.
Okay, thanks for that question, Lisa. Some more questions here. This one, again, from Donald Primary School. How close can you get to an active volcano? And I'll let, again, we're going to let Ceinwen answer some of these questions.
Well, you don't want to get too close to some erupting volcanoes, I can assure you. We saw some video before of some people in Hawaii, and they were getting very close to the lava flowing along the surface. Now, most people there aren't too worried about danger around the volcano. In other areas like Mount St. Helens, which we saw erupting earlier, and Mount Ruapehu, they're much more dangerous eruptions because they're more explosive, and so you would want to stay kilometres and kilometres away from those volcanoes. I certainly wouldn't be running towards them at the time they were erupting.
I think the thing to remember is when you're near one of these things, go to the local ranger or some local person who is in charge of that area and ask about those questions. You want a professional to tell you how close or how not close you can get. Another question we have here is, how do you know what the inside of the Earth looks like right down to the core? And this is again from Andrew at Donald Primary School.
Okay, the reason that we know about parts of the Earth that we can't actually get into are the rocks that we see thrown out, like the rocks that we've seen thrown out of the mantle. But the actual core itself, we haven't actually seen it. We can't get down there. And what we have are special machines that are like X-rays, and we can actually take pictures of the inside of the Earth, and we can see that there's different parts which have different densities, so they weigh different amounts, and we can see that there's changes. So we imagine that there are things there. We can't actually prove it, but this is our best theory, as we were talking about before.
And we're able to take one more question before the end of the program, and we take it because it leads on to next week's program, which will be along in a couple of weeks. The question comes from the grade 5 and 6 students at St. Andrew's Private School. Can tektites only be formed by an asteroid? And I'll let Ceinwen finish off with this question.
Thanks again. Okay, they don't have to be always formed by asteroids. Perhaps we should just define tektites first. Do you want to just take that quickly and define that?
I'll let you do that.
Okay. Well, a tektite is a shocked type of glass, and we think that these might be able to form from volcanic eruptions as well as from asteroids landing on the Earth's surface and shocking the mineral from just compression from the asteroid landing. So these can be formed in volcanic eruptions, and they might also be formed by asteroids landing.
So in next time's program, which will be along in a fortnight, we'll take that question up and look at tektites and volcanoes and extraterrestrial visitors, not aliens, but certainly things that have come in contact with the Earth that have had an effect, or we think have had an effect on dinosaurs. Thank you for all those questions, and we'll look forward to seeing you all in about a fortnight's time.